Let's talk about now real reactions. So very often in this course you have seen a chemical reaction where there is, if you will, a lot of reactants and a lot of products. And we have been talking about chemical reactions as that chemical process that happens at the molecular level where molecules need to collide, and that's very important. So if you think that this reaction in which there is 1 plus 14, 15 plus 6, it's 21, well, actually this should be electrons, so let's not count this one, but it's 15 molecules. Well, how can you make collide 15 molecules, all of them at the same time? That's the probability, even for 3 molecules to be colliding in the space. That's a very low chance. Think of it on a pool table. So you get together with 2 other friends, and the 3 of you decide to throw a ball on the pool table and should collide the 3 of them at the same time. You will see how difficult that is. It's not easy to collide 3 pool table balls on at the same time. So the same happens for molecules. It means that whatever the reaction is, it does not involve colliding 15 molecules, all of them at the same time in the space. So it means that we'll have to split this overall reaction. We'll have to split into something that we call elementary steps. An overall reaction that you write will be a combination of elementary steps that actually shows how many collisions on each step you have. The combination of elementary steps is what we call a reaction mechanism. And that's something that we are going to study now, because it's just for the sake of understanding that it cannot be that more than 2 molecules can collide in the space or even in solution, unless it's a solvent, because of the unlikelihood of that fact. So let's start with a very simple mechanism. What you see here is a mechanism. It's a reaction mechanism where each of these steps is called an elementary step. An elementary step. So this reaction mechanism contains 2 elementary steps, and the elementary step, when you add it up, should be able to give you the overall reaction. So let's do that. If you try to add up the overall reaction, so you have hydrogen on one side and it doesn't show up anywhere else, 2 hydrogen chlorides in here, so you have it, this will be our reactants. Notice that hydrogen iodide shows up both as reactants and products, so that it cancels out, doesn't show up in the overall reaction. 2 molecules of hydrogen chloride and 1 molecule coming from here of iodine. Well, this substance, the hydrogen iodide, that appears in one step but disappears in a subsequent step, it's called an intermediate. And intermediates are a species that only exist during the reaction, but they are not either products, not even reactants. It is easy to identify the intermediates because they will first appear and then will cancel out by this and disappear. Okay, let's talk a little bit more about the elementary steps. Think of, from now on, when you see a reaction, that reaction should have a reaction mechanism that is typically unknown to us. We may know what we mix, so we know the reactants. We can measure what we collect, that will be our products. Usually the mechanism, the path through which reactants become products, is fairly unknown. However, we have some tools to figure out what those steps may be. So the elementary steps are of different kinds. Each of them will have their own rate law, and each of them will have their own activation energy. So you can think of a reaction mechanism as a sequence of small reactions, one after the other. What kinds of steps do we have? We have the unimolecular, bimolecular, or termomolecular, depending on how many molecules collide in reactants. Unimolecular, as it says, there's just one reactant, and the rate law is very easy to figure out. If you remember, we spent a fair amount of time trying to figure out the orders and trying to figure out the dependence of concentration on the rate. If if, and that's a big if it's an elementary step, we can figure out the rate law right away. The rate law will be a constant times the concentrations of your reactants. If you have a unimolecular reaction, the rate law is a first order depending only on concentration of that reactant. If you have the collision of two reactants, again, it'll be a second order. Okay, hopefully you get the idea. You can have two kinds of bimolecular reactions because the reactants can be either the same molecule or two, and rarely you will have a termolecular because, as we said, it's very unlikely that in one elementary step three molecules collide, all of them at the same time. Okay, if that were the case, which is uncommon, this would be the rate law. So let's practice a little bit so that you get a little bit the idea of what kind of questions we can ask you regarding the concepts we just learned. For example, if you're given a mechanism like this one, it's a typical question to being asked the overall balanced equation. And to do that, you just need to add up the elementary steps. These two elementary steps, notice that they are all feasible because you don't have more than 2 or 3 molecules colliding. How does one add up? Well, I have 2 of this NO2Cl. So I'll have just adding this up. Chlorine atom appears and then disappears, so it will not show up in the overall reaction. And you have two molecules of nitrogen monoxide and 1 molecule of chlorine. Notice that even though you have only 2 molecules here, you have 3 here. It's unlikely that 3 molecules could become, in this case, reactants. So this is the overall reaction for our mechanism. It's asking for determining the molecularity of each step. I remind you the molecularity is the name that gives you how many reactants are involved in that elementary step. Unimolecular, bimolecular. So this one, the first one is unimolecular and the second one is bimolecular. The rate law for each step, the rate law for the first one would be one kinetic constant times the concentration of nitrosyl chloride, and the rate law for the second elementary step would be another rate constant times the concentration of nitrosyl chloride times chlorine. So notice that in this case the concentration of the intermediate, by the way, the identified intermediates, yes, there is one and it's chlorine. Okay. Notice that in the rate law for the second elementary step, the concentration of chlorine, which is an intermediate, shows up. That's going to be an experimental challenge because it's hard to control the concentration of intermediates, but in any case, that's in the next video. However, we will decide, well, now you know the rate of the 2 elementary steps, what is the overall rate? Like, what is the rate of this overall reaction? That's what we're going to do in the next video.